Okay, thank you. So hello everybody. So this Monday we have learned about the separate excited generator, and also we talk about principles of the shunt excited generators, which is a kind of the self-excited generators. Of course, what we talk here is the DC machines. Now today we're showing you an exercise that how to analyze the performance of the shunt excited, that is the self-excited DC generators. First, we're showing you here figure 1, the A here is a typical electric circuit representing the shunt excited motors. So here that the V here is the armature voltage. Because this is the generators, that output is the terminal voltage. This is a DC, the output is the DC. So we have the terminal voltage V here. That we have the loading currents I here. That armature currents, look at here. So the armature currents represented by the IA here. And the field coilers. So here we use the A represented field coilers. We use the capital A represent armature coilers. So the field coilers vertical positions, the armature coilers in vertical positions and the field coilers in horizontal positions. That's the general arrangement, the physical position arrangement against the armature coiler and the field coilers. So for the field coilers, by taking a field current, of course, this is the DC current, RF, which comes from the armature terminals. They produce a constant magnetic field that interacts with the rotating armature. So that induce internally AC voltage on the armature coils. Because we have arranged a rotary switch on the armatures. So that is the commutators. We call it commutators, which is the a brush, rotary switch brush, converting the internal generated AC voltage ER into the DC voltage. Therefore, in the whole circuit analysis, we fixed on the resistive voltage drops as well as the DC energies rather than the AC inductance. Here, so for the armature coilers, we're using the RA here represent the inclusive armature resistance, which may include 1, the armature coilers itself's resistance, 2, the interpole coilers resistance in series, 3, the compensation coilers resistance, and 4, the brush touch resistance. So RE here is the total resistance of above factors. For the field coilers, we have the so-called resistance RF here. So in the lectures, we already explained the RF actually comes from 2 parts. One is the field coil itself. The field coil itself has resistance. The second part is rheostat. That means the adjustable resistance to control the field currents against the terminal voltage. So anyway, we're here using the RF represented. So the terminal voltage F, which also is the field circuit voltage VF, related to the field current RA through the resistance RF. So their relationship be a linear relationship. That's the straight line here we show here. So the field, the field current RF here This is the field current IF, right? Okay, this field current IF. This is the ER, right? Internal ER. Okay. So the relationship when it is open circuit between the field current RF and the internal generated voltage, therefore the terminal voltage is a straight line, which is this one, straight line. Okay. On the other side, the excitation, internal excited, right, voltage ER against the field currents is shown by this curve. Okay, shown by this curve, which we explained in the lectures. The starting point is not zero values because the residual flux in the self-excited generators. For the self-excited generators, we have to have certain level of the residual flux so that the machines can start right automatically. And the curve here actually is the excitation curve. It's the BH curve actually. Okay. So when you change the field currents, the internal generated voltage changes against the beat. So, which also we explained in detail in the lectures there. Now, so based on these two figures, we have the following equations describing the relationships between the field voltage, field current, field resistance, and armature currents, armature voltage, armature resistance, and internal rotor rotation speed and generated voltage and armature currents, and so on. So therefore, with understanding of the above figures and the symbols we marked on the figures, we have the this kind of the voltage equations. The first one, the terminal voltage V equal the armature voltage VA equal the field circuit voltage VA, which actually can be seen obviously from the figure A. And related to the field circuit, in the field circuit, the field current IF, the field circuit has the total resistance RF. So this is voltage equations that can be easily figured out from the circuit. And also the loading currents I here equal to the armature currents minus the field currents. That's it. Okay. In the armature circuit, armature, in the armature circuit, the armature voltage VA equal to the internal generated voltage ER here, which is the DC, root mean square values of the internal AC here, is the DC. ER minus the armature voltage drops, which is the products of the armature current IA and the armature total resistance RA. Then, so on the other side, taking account the internal generations, the internal generated voltage ER related to the rotor speed omega R and field current RA with a coefficient K. So this look that this is the key for generations. This is a key issue, right? So this is the we say actually Lane's law, inductions, inductions issues. So the original Lane's law formulas is not like this one, but we know that the moving a conductors inside a constant magnetic field or relative changes of the magnetic field against conductors. So that's the principles. Applying to the rotors here, So we have these formulas. And this is this curve. Okay, it's this curve. Okay, and the so the armature current, which is the so sum of the loading current plus the field currents. So armature currents is the maximum one. Okay. So the armature resistance. So these three represent the relationship between the terminal voltage, armature voltage, field circuit voltage, armature currents, loading currents, and field currents, as well as the internal generations. Okay. So all the following equations just is derived from above three for specific purpose. For examples, if you like to study about the generator's load characteristics in terms of the loading voltage, loading current against the internal generations, then you can find out how does the loading current change against the internal parameters. And two, how does the terminal voltage change against the internal parameters. So we can combine about three equations so that to relate. One, the loading currents. Look at here, I is loading currents, which, the loading currents here, loading currents, I here. So from here, the loading currents, is the internal generated voltage, minus the field circuit resistance, the armature circuit resistance, times the field currents, then overall, over the armature resistance. So this easily can be derived from above one. So you're just looking at here, so you can got from here. You just change here. So from these equations, you can got this one. Okay. So change these equations that you have the I here, you have RF here. So here, this is the ER. So just the ER, minus the minus the RF, times RE. Okay, so for the voltage V here, so it comes from the VA. So voltage V, which equal to V, A, which equal to this one. Then look at here. So the terminal voltage, terminal currents, when the terminal currents, so is given, internal resistance is given, the terminal voltage given. So then, for the internal rotation, it determines the internal generated voltage here. So meantime, so because the internal generated voltage and the field, so the loading currents, the loading current causing some voltage drops on the armatures. So the terminal voltage changing with the loading currents. Okay, so generally speaking, that when the loading voltage, right, loading currents increases, that the terminal voltage will decrease, right, if the internal generator voltage is fixed. But this is not so obvious, because that when the internal generator voltage changing, when the terminal voltage changing, that's the field current will change. So the field current changing, therefore causing the change of the internal generator voltage. So what's the obvious relation between them? We cannot, right, looking out from the formulas here, So we should to draw some figures to see how does the loading currents change, How does the terminal voltage change against loading currents? Now, generally, to make the things be simple, we know that the armature resistance, because the armature usually is a big coilers there, so resistance much smaller than the field circuit resistance. That means the RA much smaller than the RF. This is generally true. I still remember that in the lectures that for the RF may be 50 ohms, but RA may be just 0.2 ohms. So 50 ohms, 0.2 ohms is totally different. So in such a way that against the RA can be right in load when it is plus together with RF. So then the above equations can be simplified as the terminal current equal to the internal generator voltage minus the RF over the RA. So you look at that, the RA usually much smaller than the RF. So as a result, that the loading current may be much bigger than RF. It depends, right? So the terminal voltage now, which can be simplified as the V equal to ER minus IRA, because we suppose the RA much smaller than the RF. So the RF over RA plus RA can be equivalent, can be approximately equal to 1. That's what we have. So as such, we have this loading current and the terminal voltage equations, which are very simple. From this one, so we can showing you the general relationships between the loading current and the terminal voltage. So here is the excitation process, that the field currents which are changing with the internal generator voltage ER. So the ER, this CR. So when the field current changing, this ER. This is the excitation curve, curves. This is the straight line that represents the field circuit. Field circuit. Now, in general, if we so at the beginning, if the loading current be 0, so loading current, this is loading current be 0, then the internal generator voltage, therefore the terminal voltage, terminal will be different. So the solid line for your easy understanding that in this figures that we have the solid line, we have the dashed line here. So the solid line represents the ER, internal generator voltage, against the field current, as well against the armature currents. So A is the voltage ER against the field current, and the V against the field currents. Straight line is the V against the field currents. By straight line, okay. Okay. Okay, that's the meaning of it. So, because this is self-excited generators, that when the loading current changing, that terminal voltage changing, that field current changing, that internal generator voltage changing. Okay, so that's the relationships. So it is not straight line, and as you look here, okay. So because the ER against the field currents is not just straight line. Okay, so which should be described by a curve like this, and the V to the field current, which is the straight line. Okay, look at it here. Okay, V, okay, V to the field circuit is a straight line. Straight line. Okay, non-straight line. Okay, that's mean. Okay. So for the VIF straight line, for the K omega RIF, this is curves like this. As a result, so at the beginning, so when the loading current is 0, loading current very smaller. Generally, when you start it, there is loading currents. Okay, so the armature currents, loading currents, the same. Well, when the okay, so then when you start it, okay, so as the loading current increases, okay, the field current also increase, okay, field current increase, and the generated voltage increase, okay, which along the solid line like this here. So when the armature current increase, then when the loading current increase, that means the armature current increase, and the field currents also increase, generated voltage increase. Meanwhile, that there is the armature voltage drops increase. At certain levels, the terminal voltage, okay, will be reach the maximum values. After that, okay, the voltage will decrease again when the loading current increase. That means there is upper limits of the loading currents. Okay, upper limits of loading currents. So when the currents larger than these points, the machine will automatically slow down. Okay, this overloading areas. So generally, we make the machines work in these areas. Okay, so the current larger than these points, so we are making the machine stopped. Okay, that's the meaning of it here. Okay, so of course, someone said, why you know that the curve like this? The next slide, we are showing you that by giving specific figures in the questions, we can gauge the curves like this. So here, just to show you the general possible relationship between the terminal voltage and the internal generated voltage and the terminal currents. Okay, so this is my explanations on the figures given here. So such a curve telling you that the self-excited generator has the self-protection functions when it is overloaded or short circuit. So the machine will stopped. Although the internal voltage generated is very high, but the current will get down quickly. Okay, so now we're looking at specific examples to see what's the performance of a given generators. Meanwhile, try to understanding the meanings of the figures given in the next questions. Okay, now given that we have a machine shunt generator that has a 17.5 kilowatt 110 volt shunt generator. What does this mean? So this is a DC generator. So the rating output powers is 17.5 kilowatt. That's the meaning of it. And the rating terminal voltage is 110 volts. The shunt generator excited has a field circuit resistance RF equal to 100 ohms and an armature resistance of RA 0.1 ohms. Okay. That's why in the above slide we assume that RA much smaller than the RF. That's true in practice. So the magnetizing characteristics at rated speed is given in figure 3a. So that's this one. This is the excitation curves, for a given speed, rating speed. Because the speed changing, that's so the generated voltage also changes. Here, suppose the speed be fixed at a certain levels. Now, determine the critical field circuit resistance RC and the load characteristics V terminal voltage versus loading currents. That's the meaning of it. Load characteristics means the loading voltage and loading current relationship between them. Okay. So what does it mean by the critical resistance? We explain the definitions of the critical resistance in the lectures. That is the maximum excitation circuit total resistance anode. The maximum values of the RF anode, of the RF plus RA anode. Here we using the small one. Okay, the meaning of it. Here for a reminder. So the critical field circuit resistance RC, that is the maximum RA plus RF anode for a self-excited machine. Because the RA usually is much smaller than RF, so it also can be seen roughly that the maximum field resistance allowed for self-excited machine. Okay, so according to the the curves given here, so from the curves, because the divisions given for the vertical and horizontal one, the horizontal is field current RF, the vertical is the ER. So from the curves, one can simply find out that so when the field current be 0.4, 0.4, that the armature, sorry, the internal generated voltage is about 80, right? About 80. So that is the resistance is the voltage over the currents, right? So 80 over 0.4. It's not smaller than 80 over 0.4, which is smaller than 200, but larger than 180. So the values actually is given here is 190, right? Ohms, 190 ohms. Now the RF resistance, which is the 100 ohms given. That's the meaning of it. Okay. So loading characteristics. In the above slide, we already have the equations 1 and equation 2. Therefore, here we just break in the values into the above equations. So there, the current equal to the terminal current equal to the internal generated voltage minus the armature resistance times the field resistance armature field resistance times the current field currents over the RA. Because the equations in above right slide that given that relationship between the currents equal to the ER minus RA IF over RA. RA given here is 0.1, so that's why 1 over 0. That's why we have the n. We have the 10 here, and the RF given 100 ohms. So 100 ohms over 0.1, that is 1,000. That's the mean of it. So 10 ER minus 1,000 RF. That is it. Okay, so the voltage equal to the internal voltage minus B equal to ER minus RA times I. We bring in that, so V equal to the ER minus 0.1, that is RA values, which is given, that times a terminal voltage, a current I, that's it. Okay, so the following tables then is drawn up for a series of the values of the field current IF and internal generated voltage ER, which can be read from the curves given here. First, so for the field currents, for the field currents on the horizontal one, on the horizontal one. For example, if the field currents is 0.1, 1/3 of it, so you can find out the voltage here. So then that this is this points, 1 point, 3, that's we say here, that the voltage will be 150 by 3. And also, you can have these points, so and so on, so on. So therefore, so IF here and ER here follows these curves. From these curves, okay, this is the reflected in these tables. Okay. So then, for a given E, right, internal generated voltage with right, for examples, for the field current 1.33 amperes here, it corresponding to an internal generated voltage 133 voltage, right here. And suppose the loading current be zero, then the voltage, okay, the voltage, terminal voltage will be equal to the right ER. That's this point. That's this point. Okay. If the field current be 1.1 amperes, for example, something like here 1 amperes, then the so the internal generated voltage will be 126 volts. Okay. Corresponding, okay, the corresponding that, okay, these points, okay. So internal voltage, the terminal voltage, and the loading currents, okay, no loading currents, because that here, if the IF, okay, equal to 1.1, IF equal to 1.1, okay, and the internal generated voltage will be 126, 126, 101, 126, and you can calculate the loading current I will be 160 amperes, 160 amperes. So with the 160 amperes bring in here and the internal generated voltage 126, you can get the terminal voltage V, which is smaller than, okay, the 126, which is about 110. So that's this one. Similarly, for the field current, okay, 0.6 amperes, field current 0.6 amperes, and from the curves here, the internal generated voltage 100 volts. So 0.6 amperes, 100 volts. Bring this in. 0.6 amperes, 100 volts. Then you can gauge the currents. That currents, okay, 0.6. That this will be 60. 100, okay, 100. So you can find that the loading current will be 400 amperes. 400 amperes. So loading current will be 400 amperes. Okay. So meanwhile, that for 400 amperes here, 400 amperes here, and for the internal generated voltage 100 volts, 400 amperes, 100 volts, the terminal voltage can be estimated, okay, 60 volts, because 400, okay, 100, this is 40, okay, 100 minus 40 is 60, so 60 volts. So you have the 60 volts. This is the 60 volts. Okay, loading current of 60 volts. After that, if the field current be 0.5 amperes, becomes smaller, 0.5 amperes, okay, and from here 0.5 amperes, the internal generated voltage will be larger than 80 but smaller than 100. Okay, so larger than 80, which is smaller than 100, which is really 88 volts. Okay, so 0.5 RF, ER 0.88 volts. So 0.5 amperes, 88 volts. Bring in, okay, you can gauge the currents. So because, okay, maybe some students later ask why we have these currents. So we have these currents, we estimated, so 0.5, 88. Okay, 88, 0.5, okay, minus 0.5, okay, this is 500, right? 88, this is 880, okay, minus 500, 300, right? 80, right? 380. So we have the field current, armature current, 380 amperes. 380. So 380 amperes, okay, times 0.1, 38 volts. So this internal 88. 88 minus 38, that is 50. So that's the 50. Okay, that's the 50. So we draw the 50 here. This will be 50 here. Okay, something like this. Okay, corresponding to 280. Until that, okay, when the field current be 0.1 amperes, field current be 0.1 amperes, corresponding to values of the internal voltage 20, okay, volts. So 0.1, 20. Okay, so 0.1, okay, this means 100, 20, 200. So 200 minus 100, this is 100. So the terminal currents or the loading currents will be 100. Okay, will be 100 amperes. So with 100 amperes bring in here, voltage drop will be 10 volts and the internal 20 volts. So the terminal voltage will be 10 volts. That's the terminal voltage will be 10 volts. So when the armature current be 100, so here, that's this point. Okay, that's this point. So you look at that. So we exactly following the equations we listed above, okay, in these equations, and these two equations. We first giving field currents corresponding to the field currents from these curves. We can check about the internal generated voltage with the field current given and the internal generated voltage. We can estimate the loading currents. With the loading currents here, we can estimate, right, loading currents and the internal generated voltage. We can estimate terminal voltage. And then we can draw the relationships between the terminal voltage against the terminal currents like this. So this is these generators, okay, loading characteristics. That is the terminal voltage versus loading levels. Okay, so this is the general approach analyzing the loading characteristics of self-excited DC machines. As a matter of fact, right, so we also can use the similar approach to analyze the self-excited motors, okay, performance. Since we not yet study about the motors characteristic analysis, so we will, right, deliver the analysis, the motor performance in next week. Okay, in next week. Okay, so that's the today's tutorial. So today's tutorial performed to you how to analyze the self-excited generators performance based on their parameters given. So these two figures show the general characteristics of the self-excited generators. The left side, the curve, solid line curve here, usually represent a typical excitation curve relating the relationship between the field current and the internal generated voltage. Generally, for a given field circuit, we have a straight line like this, which is smaller than the critical values, right? The slope smaller than critical values given here. Okay, the field, right, circuit resistance 100 ohms, while the critical values 190 ohms. Smaller than this one means that the machine can self-excite. Okay. Then, we based on the circuit, we can find out the relationships between the terminal voltage and the terminal loading levels. Okay. So we show in the right side of these figures. This is a general case, general case of the possible relationships. So in practice, when you adjust the field, right, current, adjust the field current, then the terminal voltage will change it, and the terminal loading levels will change also like this. So anyway, so you look, this is not straight line, this is a curves. These scripts. Okay, so you may take some time to digest this one. Okay. So, any questions on the DC generators, or we say the shunt excited generators? You can write down in the chat box, or you also can write to me via the emails after lectures. So it seems that you have no more right questions on it. So that means that you all are smart enough to understanding what are delivered here. Okay, so if you have no more questions on these examples, of course you can still have time to read it after lectures. So then I will end these sessions. Thank you all for attending today's tutorial.